Welcome to our next talk. It's real cloud native with serverless Java. Thanks for joining. So this talk is all about how we can build modern systems in the cloud very easily. And this is also a kind of like journey through the history of software development and how the infrastructure is evolving. So, similar to yesterday, I have a gift for you, first of all. So, if you are interested in joining an online course, you can book a course for free. It's sponsored by MicroStream and Java Pro Magazine. So, we provide Open Liberty courses, Payara Micro, Micronaut, GraalVM, native images, Spring Boot, and Quarkus. Take a photo, check out which date fits best for you, then you can enroll. We have around 100 seats for free. And of course, you can submit it to your friends and colleagues, invite them also. My name is Markus Kett. I'm CEO and co-founder of MicroStream. We are super proud to be also contributor to Project Helidon and to Micronaut. And by the way, currently I have to compete with my friend Sergio from the Micronaut team, who has a talk at the same time. So we are also involved in the Rapid Clips open source project. So it's a kind of like visual basic for Java. We started this project around 15 years ago, and so my technical background is we're building software development environments since almost 15 years now. And so the challenge always was improving and simplifying database programming with Java. And this is also the reason why we started the MicroStream open source project. So Rapid Clips is also free, and we're gonna start a Eclipse project soon, so you can check it out and build software easily. So the IT is currently changing. It's changing all the time, but we have several revolutionary changes the last years, and one of the most important changes, of course, are container. So we started with physical servers around 20 years ago or so, and then the virtual servers came up, and this was really changing everything. So we were able now to run more application and one in the same server and share the resources. But then Docker introduced containers, and so we were able to use our resources even more efficiently. And I can remember my first Docker talk at Java 1, and so this was at the beginning very complicated to use Docker, and then the speaker said, soon there will be a platform that will do the job for you. So he talks, of course, about Kubernetes, but was still unknown. Then we get the Kubernetes platform to manage containers, and with containers and Kubernetes, also software development changes. But in the cloud, there was further challenges and changes, and one of the most important changes, so this is my personal opinion, is the possibility to create infrastructure as code and, of course, horizontally scaling systems. So actually, we want to build systems that scale horizontally, fully automated. So, but the problem or the challenges in practice are the systems really able to scale horizontally automatically. So actually, this is the goal. What does this mean? So here is an example for vertical scaling. So let's say we have a server running, application server running, and we have a normal load, then everything is okay. But if the load goes up, then this system is in trouble. So, and actually what we have to do now, we have shut down the system. We have to define new resources for our application, restart the system that now has much more resources, and then everything is fine, so great. But the problem is now it's also not efficient. It's because mostly we have defined too much resources, so which means it's not perfect. And if the load now goes down, then this system is too big. So, and we waste much money in the cloud. So, horizontally scaling is much better. And actually, this is our goal, to build systems that are really able to scale horizontally seamlessly. What does this mean? So this is our system, and if the load goes up, the system is in trouble. But now our system is able to start new nodes and multiple nodes that share the load. Now the workload goes down, the system is more cost efficient. So, and we are able to start multiple machines, and we scale horizontally. So it depends on how you configure the system, how many loads can be started by the system. So it depends actually only on your budget, right? So if you have enough budget, you can scale unlimited. Mostly it's not the case, so be careful what you're doing in the cloud, because it can be very expensive. So you need monitoring and alerts and something like that. If the load goes down, then we expect that the system automatically shuts down the machines. They are not required anymore, and we save infrastructure costs, and so on. If the load goes down, system shuts down machines. They are not required anymore. If the load again goes up, system starts the new machines. So, and this depends on the workload. It can be that it's once in a year or once a day, and so this is actually a great system that is highly cost efficient. But also building highly scalable systems is challenging in the cloud. But let's talk about this later. Microservices are also changing the way we build systems. And who of you develops actually microservices even today? Okay, so many developers today still building monolithic applications, and that's absolutely fine. So what we're doing with microservices is, in a monolithic application, everything is really simple because it's everything is in one and the same system. And with microservices now, we cut the monolith and split the monolith in numbers of services that run completely independently. So microservices is really great, but also absolutely challenging, because developing microservices is fundamentally different to monolithic applications. And also the Java stack will change completely. Then all of these microservices should run in their own container. So there are some rules with microservices. They run in their own container independently, and each microservice should have its own storage and so on. All these services run on a platform, on a container platform like Kubernetes, of course. What's challenging with microservices? So as I mentioned, with microservices, the Java stack changes completely. So why? It's because with monolithic applications, we were used to use application servers. Application servers were built to run on big machines and to run multiple Java applications in one and the same server. And the server was started once and run for years without shutting down the entire system. So they have mostly high memory consumption, slow startup time, because this fast startup time was not that important. And also the JVM, so we of course used to use the JVM for executing Java applications. And the JVM is absolutely great because we have this JIT compiler that accelerates applications tremendously. So at the beginning, Java was known as slow, but in comparison to C. But now with the JIT compiler, it's really, really fast. But the JVM has a slow startup time and a high memory consumption at the beginning, so at the startup time. So is this suitable for microservices? Is the question. And the answer is no, this is actually not suited for microservices, because with microservices, we have these containers, and containers can fail all the time. So we have to restart the containers, and we need fast startup time. And this is the reason why now we don't use application servers anymore. We don't run multiple applications in one and the same container. We run only one service in the container, which means now we need a runtime that is suited to run only one super small Java application. And this is the reason why we now use the microservice frameworks. So all of these application server vendors, they build their microservice runtime, so microservice framework. And here is an overview about all of these micro runtimes, as they are called also. You have the two worlds, Spring and Java Enterprise, which is now called Jakarta EE. We had these classic application servers, and now all vendors provide their own microservice runtimes. And the standard, the previous standard for monolithic applications was Jakarta EE, Java Enterprise Edition, and now we have microprofile as a new standard for micro runtimes. And here we have the frameworks that follow the microprofile standard and implement the microprofile standard, like Helidon MP, Payara, for instance, and Open Liberty. I'm not sure if Quarkus follows the microprofile standard, so but I have Quarkus on the list. And by the way, Helidon is the only framework that provides actually two frameworks in one. So we have the other frameworks that do not follow and implement the microprofile standard, like Micronaut or Helidon SE, which is a reactive framework. So they are built to be even faster, and here the goal is nothing but startup time. So to start your service as fast as possible in milliseconds, that the system is able to manage the load without any delays and without any latencies. And of course, with Spring, we have Spring Boot. So, as I mentioned, the Java virtual machine is absolutely great, but it has a slow startup time. It's because JIT optimization, this takes some time, and then the memory consumption goes down and becomes super fast. Now with GraalVM, Oracle introduces a completely new technology that is also built for polyglot programming, but I guess it's not that interesting for Java developers. Or is anybody interested in polyglot programming? So, yes. Two guys. It's interesting, but not that important for Java developers. Mostly more interesting is the native image function, which allows to compile a native image that starts instantly. And this is absolutely great and a game changer for us in Java. So because at the beginning of this container and microservice architecture, it was really the question, is Java suited for building fast microservices? So this was really a challenge. But with native GraalVM native image, we have now, these are numbers from Oracle, 50x faster startup time and 5x lower memory consumption. This is great. But it's also challenging. Who of you uses GraalVM native images in production? Same guy. Only one? Really? Two. The reason might be it's challenging. So and you have some trade-offs with GraalVM native images. And so my question to you: how do you build microservices without using GraalVM native images? Because you need super fast startup time. Nobody uses microservices in production, right? We have now a great JDK project. So when I heard it for the first time, I was really surprised. And the Open JDK project Crack, super interesting. And here the JVM is now able to persist the current state of your JVM that is optimized by the JIT compiler, so you can persist it. And when your microservice starts again, then the JVM is able to restore the system state, which means it restores the optimized JIT compilation state. And we get instant startup times without GraalVM native images. And we can define when we want to persist the system state of the JVM. And so the startup time with this project Crack is really fast. So, and for me personally, I think in most projects we won't need GraalVM native images anymore. And yeah, this functionality is implemented by almost all JVMs. So OpenJ9 JVM supports it. Azul has introduced this technology and has started this OpenJDK project Crack. So with Azul, you also get it, and with Azul Prime, it's even more fast. So it's, you can check it out and play around if this fits for you. But very interesting. And it's absolutely game changer for microservice development with Java. Also persistence. Persistence is also challenging, of course, and is changing. So with NoSQL databases, we rethink database development, because now the NoSQL databases introduce completely new data structure and formats. And I believe they are so successful because they scale horizontally much better than SQL databases, because relational model scales very well vertically. And the NoSQL databases with the data structure, let's say key value, it's built for scaling horizontally very well. And also traditional databases cannot keep pace and lead to high complexity in the cloud and expensive infrastructure. And the reason for that is it's because it's not possible to store object graphs and Java objects seamlessly in a relational database, because the data structure are incompatible. We have several impedance mismatches here, so you can read more about this in the internet. So you'll find lots of articles, also a great article on Wikipedia. But these data structures are incompatible from a technical perspective. But it's the same with NoSQL databases because native Java objects or object graphs are incompatible with most of these NoSQL database data structures, like JSON-based databases or graph databases and even object-oriented databases from the 1990s. So they introduced their own proprietary data structure, and they are incompatible with native Java object graphs. And to solve this problem, we need for relational databases, object relational mapping between the application and the database. And if you use a NoSQL database, you need a kind of like data conversion through every single read and write. And when we measure the time, how long does it take to generate the objects by object relational mapper, then you will see it doubles your query time. And this leads to expensive latencies, you need additional CPU power, and so the costs will go up. To accelerate queries, we are used to use a cache. So cache is in-memory, data are in-memory, so this is fine. And reading data directly from the cache should be much faster than accessing a traditional database that has access to disk. The problem is with local caches, if you run a distributed application, then you start multiple machines, and if one of these nodes changes an object and stores this object back in the database, then the node and the database are in sync, but all of the other nodes are not in sync with the database. So we have a problem here in terms of consistency. What we can do, or in practice, we can put the cache between the application nodes and the database. So we have now another layer. We can add a caching layer. And in the cloud, we should avoid single point of failures, which means we also want to run a distributed system here. So let's run a distributed cache. So this means our system complexity increases. And if the load goes up, then it might be a good idea also to cluster the database. So we add another cluster here. So finally we have 3 clusters running, lots of machines, lots of CPU power, high cost of infrastructure, but it's common today. With the MicroStream open source project, we try to simplify data storage and database development, speed, and try to reduce the cost of infrastructure. So we say that in-memory computing is, of course, very fast because it's accessing memories up to 1000x faster than accessing a disk. So let's do everything in memory, and Java is built for in-memory computing. So everything that is executed in memory with Java will be super fast because of our JIT compiler. So we have great programming language and high-speed performance with Java, with Gravian native images also. And we have a great data structure. So the database vendors are still searching for the perfect data structure. And because with microservices now, we split our monolithic application, and each microservice should be responsible for specific use cases. And all of these use cases, they deal with perhaps different data. So perhaps we need different data structure. If you have machine data, then perhaps a time series database would be suited. If you have complex relations between our data, perhaps a graph database would be better approach. But with Java, we actually have already a multi-model data structure, because with an object graph, we can store almost everything. So we can store simple objects, we can store key values, we can create highly complex object graph with circular references. So We can use all Java types, collections. We can create our own indexes. Perfect data structure. And with Java version 8, Streams API, we have a query language for searching object graphs and filtering. And if you use Streams API, you will get microsecond query time. So it will take only microseconds to search on an object graph in memory. 1000x faster than a comparable JPA query. The problem so far was Java does not introduce a functionality to store object graphs seamlessly. So for storing objects, as mentioned, we use databases. They are incompatible to Java object graphs, and this leads to delays. But what if we would be able now to persist Java object graphs seamlessly as they are in the memory? So we can follow the system prevalence pattern, which says that we can keep the system state in memory, query and search in memory. Everything is very fast, and just create a snapshot of your system state and restore it when the system restarts. Simple architecture, but there are also many challenges, and this might be the reason why this concept is not used in practice. With MicroStream, we have now solved all of these problems and so answer all of these open questions in terms of system prevalence. In a nutshell, MicroStream is a Java native persistence layer that enables you to store any kind of object graph, any complexity, any size, with no limits in terms of the depth of your object graph. You can use all Java types, create whatever you want, and MicroStream will be able to persist it. And vice versa, when you start your application or your microservice, MicroStream is able to restore, to reload your object graph and restore it in memory, but not loading the complete system state, and not to load the entire database into the memory. By using lazy loading, you can avoid this, and you can load single subgraphs when they are needed. So you can deal with small memory sizes and run micro machines that you need for microservices. The complete API is open source, and the code is on GitHub. You can download it via Maven. It's just a Java API and runs within the same JVM process of your application or microservice. It's integrated with Helidon. We have great integration with Helidon and also with Micronaut. So if you use Helidon or Micronaut, you get MicroStream out of the box. So how does this work? What we have done is actually, let's have a look into the database. Because mostly database is a black box, nobody thinks about how does database actually works inside. So we have here business logic. If you store procedures or store functions, most Java developers don't. But database vendors, of course, they tell us put the business logic into the database. But in Java, mostly we don't. Then, of course, database also keep data in memory and cache data in memory. We have database management system and the storage data. And mostly, and it depends on the database vendor, mostly the storage data are stored in a binary format or in a human-readable format. So now with MicroStream, now we have replaced the object relational mapping layer or the data conversion because we store the object graph as it is in memory. So we don't need a object relational mapper or a data conversion anymore. And then we query the object graph in memory, which means we use the object graph in memory like an in-memory database. So we can do everything with Streams API. It's in memory already, so we don't need a local cache anymore. So we can remove it. We also don't need the database management anymore. So the business logic of your app or your service becomes now the database management system, because we care mostly in Java, we care for concurrency, logging, and locking anyway. And we keep the data storage, of course, in a binary format, because we want to persist the data in a binary format. And this is the architecture of MicroStream. You can choose also the data storage. You can use plain files, blob stores, or any database system, because they are able to store binaries. And then you can use the backup functionality of the databases, but actually it's not required. So most users use blob stores like AWS S3. It is a Java library that runs almost everywhere, in containers, in the cloud, even with GraalVM native images, and we even have an implementation for Android. The only requirement is Java version 8. All right, so at this point, I'd like to show you a small performance demo. It's a bookstore demo. You can download the code from GitHub, so you can download it, play around, implement your own queries. And here we can see two applications running in parallel. One is built with Hibernate and cache, and the other application is built with MicroStream as a persistence layer. And we execute, or we search object graph in memory. Here you can see the query code, and all queries are much faster than comparable JPA queries. So sometimes up to 1000x faster queries. This is not a MicroStream magic or so. So this is actually plain Java. It's core Java. You search object graph is Java Streams API. What MicroStream does, we persist the data and serialize data on disk. So incredible performance and with pure Java. And it fits great with microservices because MicroStream has no dependencies, no requirements to your classes, just pochos. There are no interfaces to implement, no annotations, no superclasses. So, and you can build your object model completely freely. But when we create the infrastructure, then still we have to define everything. So the machine instances, memory size, CPU, power. With serverless computing, the idea is to run applications or microservices without configuration, without the effort of creating the infrastructure. You just run the application, and the application gets the memory and the CPU power as it's needed. Because you can care for your own, of course, but running Kubernetes in practice is very effortful. So installation and base configuration is very effortful and complicated with Kubernetes. You have to define almost everything: access to your pods, security, logging, monitoring. And if you run a Kubernetes cluster, you have high base costs. Even if you don't run anything, so you have base costs with Kubernetes. There are fully managed services, so they are provided by almost all cloud providers. So, for instance, I mentioned here AWS. You can use, for instance, AWS EKS or Fargate. That simplifies running Kubernetes in production tremendously, so it's much easier. But with serverless function, it's even more easy to run your microservices in the cloud. And with serverless functions, and at the AWS, they called Lambda, you get a serverless computing platform that is event-driven. So, which means your service is called, so your serverless function is called and executed, and then it shuts down. And you pay only for what the serverless function consumes in terms of memory and CPU power. So you don't have to think about how much memory or how many CPUs should your application or your function need. So just deploy it, and then it gets the power from the infrastructure automatically. So it's a pay-as-you-go concept, and resources that are not needed, you don't have to pay for. And there are so many applications. So in most applications, we have modules. They are needed and used all the time. But there are also so many modules in applications that are used once in a year, or once a day, once a week. And so this is highly cost efficient to run these modules based on AWS Lambda serverless functions. And you don't have to run classic functions. You also can run classic applications, Java applications. So everything can run as a serverless function in AWS Lambda, also in Microsoft Azure or Oracle Cloud. And it's really easy to use. The JVM is provided by the cloud provider. So with AWS, you get Corretto as a JVM. Yeah, and you don't have to care for anything. That's great. So, and with serverless function, we are really able to save lots of infrastructure costs. Yeah, here is an example. So how it works. So the serverless function starts, it's executed, and if it's not needed, it shuts down automatically. But the problem is, if you have state in your serverless function, it has to be persisted before it shuts down. Otherwise, it will lose data. So there is some effort to do this, persisting the function state. If it shuts down, before it shuts down, it should be persisted. You can do this with serialization, for instance, or also using Hibernate. So, and if the function is called again, it will restart, so system state is loaded again, and function is executed, and you pay only the execution time. And here it's the same with persisting the system state with Hibernate. Can be effortful, heavy wide, and complicated, or more complicated than it should be. On the other hand, you can use also JSON serialization, but there are also trade-offs with JSON. If you have more complex objects, this is not possible with JSON. Circular references are not supported, and so on. And there's some boilerplate code. So what about an all-in-one platform that cares for everything, from containers, from running your application, serverless, and scaling horizontally in and out, that cares for everything? You have only to build your business logic, deploy it, and run it. And this is what we are currently building with MicroStream in-memory data cluster as a serverless cloud. What we do here is we replace a traditional the traditional application nodes with MicroStream nodes. So here we use the object graph in memory as our in-memory database. We query it with Streams API. This is absolutely fast, and here we can now we can replicate the object graph through hundreds or even more JVMs. And this means the data are already in memory. They are distributed. We don't need a distributed cache anymore. We keep the persistent data. We store in binary format in plain files or in AWS S3. So which means we don't need a database cluster anymore. We don't need a distributed cache anymore. So we save lots of machines, and it scales automatically, and you just have to deploy a jar, and then you get out automatically a distributed application or a microservice that is distributed out of the box, you don't have to do anything. It bases on Helidon or Micronaut. So you get out of the box a Helidon or Micronaut cluster. Data execution, data processing in memory is super fast, and in comparison to a classic cluster, you save lots of machine, lots of CPU power, and save lots of money, cost of infrastructure, lots of money. The MicroStream cluster and cloud is runs on AWS. So and it's completely serverless. It simplifies application development and microservice development. There are no more mappings or data conversion, no more specific requirements to your classes. You're just POCHOs. There are no specific client API required, just call REST or implement REST endpoints. And we only use core Java concepts, so we get the most out of Java. And you get a fully clustered application or microservice out of the box. In terms of performance, as I mentioned, ultra-fast in-memory data processing, microsecond query time. So with traditional databases, we talk about millisecond query time. With core Java, we have really microsecond query time. And it's no magic. This is the power of the JVM. And you can handle really tons of workloads and data throughput. Because of the savings of distributed cache and database cluster, you can invest in more memory or you save lots of infrastructure costs. The MicroStream Serverless Cloud provides you a simple setup, so you can configure it with only some mouse clicks, high availability, replication, scaling in and scale out automatically. It's fully managed and provides everything you expect from a fully managed cloud service. And it's serverless, which means you pay only what you really need and what you really use. This is completely production proof. So, for instance, one of our customers, Allianz in Munich, the insurance company, save up to 90% of infrastructure costs because of the performance improvements. But there are also challenges. So I also want to talk about the challenges with MicroStream, because all cool technologies have pros and cons. And with MicroStream, there are also challenges because it's built for Java developers. So we thought this is the missing piece of puzzle in the JDK. So everything is provided by Java, but storing object graphs, this is not provided by Java. So this is built for Java and for JVM languages. But if you're a Python developer or if you're interested in polyglot programming, then MicroStream is not the best choice for you. It's also a paradigm shift in database programming because there is no more remote database server. You send a query and then the database does the job for you and you get the results back, and the object relational mapper creates the objects. So you have your objects in memory, you can build everything. You don't have to build your application around the database, but your data are inside the JVM process of your app or a microservice. So this is a paradigm shift in database programming. You don't have to learn any new concepts. Mostly when we have great technologies that introduces high speed and great functionality, mostly the system get more complex. And we accept it because, hey, we want to have this performance. I want it. But it's completely different with MicroStream because it's core Java. It's getting even simpler with MicroStream. But there is no SQL support. So if you love to execute SQLs, then MicroStream is also not the best choice for you. But you can allow third-party applications access to your in-memory data by using GraphQL, for instance, or defining REST endpoints. And this is actually the way you should do with microservices. But in many companies, there are systems, third-party applications that want to have access directly to a database. Actually, we should not do that. But in practice, so many companies do it. So this is not possible with MicroStream, so we have to define interfaces for that. And also it's not suited for DBAs because there is no more relational data structure you can query. So this is not provided by MicroStream. It's completely open source, so it's under Eclipse public license, which means you can use it for free. You can use it for building proprietary software. So there are no requirements. You can check it out. Code is on GitHub. We have a great documentation. Play around. If it fits for you, then can save lots of infrastructure costs, or you can build systems that are really incredible fast. We prepare not only open source, this was the last step. Now we try to create a standard similar to the JPA standard, and to make the functional principle available for third-party vendors that want to build similar implementations that work similar to MicroStream. This is on the roadmap. So we talked to the Eclipse Foundation in the next few weeks about this, creating a standard, because more and more Java developers are interested in this functional principle and use it. Yeah, it comes with Micronaut and Helidon. You can check it out. And if you have any questions, visit our booth. We have the people here that write the code, so you can ask all of your technical questions and get a t-shirt. Thank you very much. Thanks for joining. We have around 2 minutes left. If you have 1 or 2 questions, perhaps we can handle 1 or 2 questions. Okay, thanks. MicroStream sounds too good to be true. Yeah, was a marketing talk. This is not true. It sounds too good. We're working on MicroStream for 10 years, and we started MicroStream after we have worked on the Hibernate JBoss Hibernate tools for Eclipse for more than 6 years to improve it, to make it easier and faster, and we cannot solve the problem because the core problem is the incompatibility between objects and relational databases. So nobody won't be able to solve this problem. So this is the reason. And we only store the object graph and reload the object graph. So there is no magic. So the performance comes from the JVM. So the object graph is not invented by MicroStream. It's core Java. Streams API is core Java. So this is the performance. And the only thing we add is we store object graphs and restore it in memory, reload it and restore it in memory. How long does it take if we store the data in S3 and reload it, use lazy loading? So it's almost the performance of your infrastructure. So MicroStream is almost that fast as your SSD drive. And if you want max powers, max speed, you can use persistent memory, for instance, which means this is much faster than SSD drive, slower than DRAM. But it's almost the performance of your infrastructure. SQL might be old, however, it can almost any SQL client and see my data. Yes, that's true. How can I analyze data with MicroStream? As I mentioned, we have no SQL support. We cannot allow third-party applications access directly to the database. And actually, this is kind of like pattern with microservices. You actually should not do that. But I know it's, in practice, many companies do that. You can use REST for that. You can use GraphQL to allow third-party applications access to your data. Learning curve with MicroStream. So MicroStream is not suited for trainers because you can only offer one-day training. So that's it. Then it's done. Because everything is core Java, MicroStream, to learn MicroStream, you only need 2 hours or 3 hours. So because the only thing is you need a MicroStream instance, then you need a root object, and then each object that is reachable from this root object can be stored by only calling one store method, and that's it. You can use all Java types, no requirements to your classes, no interfaces, no annotations, which means the learning curve is really low. Transactional. Do I have 1 minute or speaker? Transactions. It's a paradigm shift in database programming. So here, in terms of transaction, there are differences. Each store is transaction safe, which means it's an all or nothing operation. Each change on your object graph is serialized directly to disk, and this I/O operation is transaction safe. The clustered version of MicroStream will not be open source. This will be closed source, and we will add a feed to the machine, to the machines you need anyway. Okay, if you have further questions, please come to our booth. Thank you very much.